So I present about question number one. In question number one, given that copy the script and paste in MATLAB. Basically, the command is used to demonstrate basic operation with complex number, including addition, multiplication, absolute value angles, and logarithm. The result in variable further analysis or display, as you can see the output that we have attached in the slide. For question number 2, the following script shows conversion from one form to another of complex number. The function cut to whole used to transform a complex number in rectangular from Cartesian form into polar form and expected the function whole to cut does the opposite. So this could take a complex number of m obtained by adding two other complex number which is z and v. It then convert rectangular coordinate to polar coordinate and it will display a magnitude of phase of m. And finally convert the polar coordinate back to rectangular coordinate. The actual result will depend on the value of z and v used on computation. In the question number 3, the following script illustrates the graphing capability of MATLAB. It will show graphically the generation of sinusoid from a phasor. So, this could appear to create an interactive by showing rotating complex vector in one subplot and sequence on another subplot. So, we need to insert the input of frequency, amplitude, phase and visualization involved over time with paths of observes the change. The whole command are used to retain the current plot while adding new alignment.
Okay, now we're going to talk about the result of some examples for A in project 1 part 2. So as the result of simulation of example 4A, we obtained um, like from the common windows and the variable value. So this is our result. Then fs, which is sampling rate, it has size of one multiple one, and it has 8 bytes, and it is double in class. This variable is likely representing this sampling rate of the train whistle recording. The fact that it is scalar double suggests it holds a single value, possibly in hertz. For y, which is sample data, it has size of um, 10,000 to 12,880 times 1. It has 103040 bytes, and it also is double in class. The variable y is an array which 1280 rows and 1 columns, indicating it is a column vector. Each element in this vector is a data point of the sample train whistle recording, stored as double precision floating point numbers. As you can see, this slide and the slide before this slide is the variable y, which is an array which with 12880 rows and 1 column, like I said previously, indicating it is a column vectors. So this is the result of example 4B simulate. The provided MATLAB code snippet serve two main purpose, which is listening to the train signal and also plotting the train signals. For listening to the train signals, these commands play the train whistle recording represented by the variable y. The sampling rate fs is used to accurately reproduce the audio. You can hear the actual sound of the train whistles. For plotting the train signals, one of the line generates a time vector t based on the sampling rates and the length of the signals. And figure 2, so some of the commands create a figure 2, which is figure 2, and plot the train signal against time. This The grid add a grid to the plots for better visualizations. The signal is transposed y to ensure proper alignment for plotting, and y labels y bracket n and x label n. These commands label the y-axis as y bracket n and the x-axis as n in the plot. In summary, these codes allow you to both listen to the train whistle while recording and visualize it in time domain plot, which is in the figure. The plot provides insight into amplitude variations of the signals over time. Now I'm going to talk about the result of example C in part 2 of project 1. So as you can see, this is a statement of trend signal figure we obtained after the stimulations. So this MATLAB code snippet utilize the stem functions to plot 200 samples of the trend signals, n equal to 100 column to 199, which is mean by the variable in n is assigned a range of indices from 100 to 299, representing the samples to be plotted. And this result is a stem plot of a segment of the trend signals, specifically the 200 samples from the index 100 to 299. The stem plot provides a clear representation of the discrete value of the signals at each sample point. The axis limits are set to focus on the selected segment. Well, let's go to the result of example 5.1 in part 2 of project 1. So for the original script, which is y equation equal to 0.1 times cos bracket 2 pi times 2000 t bracket minus 0.8 cos bracket 2 pi times 2000 t power of 2 bracket. These original scripts generate a signal composed of a sinusoid and a chip. Save it as a WAV file named chipwave. Read the file back into the MATLAB and place the audios. The signal is a combination of a cosine wave and a chip with a sampling rate of 5000 Hz. The resulting plot shows the first 1000 samples of the read audio file. The chip's components introduce a frequency variation over time, creating a complex waveform. This script generates a signal with a cosine wave and a chip. The frequency modulations in the chips create a waveform. Distinctive waveform. The result audio might have a combination of tones and variation in pitch. The plotted segments of the audio file showcase this feature, and later we will gonna see the updated script which have different equations of y. So also the simulation result also will be different. So now we are in result of example 5.2 in part 2 of project 1. So as you can see here, the figures, which is the simulation result for the updated script, which has different y equations. The new y equation is equal to 0.5 times cos bracket 2 pi 5000 t bracket minus 0.5 times cos bracket 2 pi 5000 t power of 2 bracket. This updated MATLAB script, which with different y equation, generates a signal which with a higher frequency, sinusoid and chip. Save it as a chip wave, read the file back into the MATLAB and play the audios. The signals now consists of a cosine wave with a frequency of 5000 Hz and a chip with a quadratic frequency modulations. The higher frequency components may result in a different audible experience compared to the previous scripts. In these modified scripts, the frequency of the sinusoid and chip is increased. This could result in a higher pitch and more complex audio signals. The plot of the first 1000 samples provide a glimpse of the waveform shapes, and the audible output may have a different tonal quality compared to the original scripts. And last but not least, the parameter tuning need to be considered in this generation of signals from a scripts because experimenting with parameters such as amplitude, frequency, and modulations could yield different sonic outcomes.
Now about the second part of the project signal and system. The part I will be presenting is case 1 that titled Sound Wave Analysis. Step 1. Sound or audio file was being created and the duration was 1 minute as the exact time duration of the wave file required is not really important, but do not make the file too long or too short. Step 2. The wave file was imported to the MATLAB via workspace function and was saved as your name.mat. Step 3. Editor in MATLAB was opened and the script I was about to write was saved as mfile. Step 4. The mat file was loaded into the workspace by me. Step 5. There are two columns of data obtained and I used the first column instead of the second column. Step 6. The sampling frequency fs from the wave file was being identified. Step 7. T from sampling frequency are calculated and a vector of time t are created. Step 8. Graph of original sound signal from data file are plotted, title and axis labeling. The time axis was labeled in unit second. Step 9. Graph of first 100-second sound signal was plotted from the data file. Step 10. Zero mean random noise are being inserted into the signal file. Step 11. Graph of first 100-second sound plus noise signal are being plotted. Step 12. Sound commands in MATLAB are being used to play both signal and there are some of my comments about the signal. Step 13. Both 100-second signal and signal plus noise are being converted into frequency domain by fast Fourier transform. The final step, step 14, both frequency domain figures are plotted.
In step 5, the noisy signal was required to compute into Fourier transform because it was difficult to identify the frequency components by just looking at the signal. Then, a two-side spectrum P2 was computed and another single-side spectrum P1 was also computed based on P2 and the even value signal length L in step 6. In step 7, the frequency of single-side spectrum P1 was determined, and P1 was plotted by using frequency as the x-axis and amplitude as the y-axis. In step 8, the Fourier transform of the original signal was taken and it was uncorrupted. Besides, its exact amplitude was determined by using MATLAB. In step 9, it was required to give some comment on the Fourier transform function in MATLAB and their application with respect to the above case. Thus, as the comment, the Fourier transform function in MATLAB is used to compute the discrete Fourier transform of a sequence. It is a fast algorithm for calculating the discrete Fourier transform and is widely used in signal processing. In this case, Fourier transform is used to analyze the frequency component of the signal, especially when it is corrupted by noise. The single-side spectrum P1 is computed to visualize the frequency components more clearly.